A particular phenomenon we can come across in undamped systems is that of beating. And we're going to see this occurring when the excitation or the driving frequency is close to our natural frequency. As a rule of thumb, if they are within 15 hertz of each other or 94 radians per second of each other, we can observe this beating phenomenon happen. And what it is we're going to see that the amplitude of our response is going to build, it's going to come to some peak, and it's going to diminish. And it's going to do this in a repeating pattern. So actually what we're going to see is a third frequency happening in our response. It's going to be oscillating at the natural frequency, the driving frequency, and this beat frequency. And the beat frequency is going to be the absolute difference between the natural frequency and the driving frequency. So we can look at this in a quick example and observe this beating occurring when the natural frequency and the driving frequency are close together. So we'll look at a simple problem where we're just going to be given our system parameters right off the bat. We don't have to do anything in the way of modeling, and we can quickly get to our solution. So we're not going to go through the full solution process here. We'll have just a spring mass system, 1 degree of freedom. We'll work without units here, but let's just assume everything's in base units. K of 250, M of 5, and here is our forcing 3 cosine 1.05 natural frequency times time. So we're going to be driving this at 5% higher than the natural frequency, and we want to see what the response is going to look like. All right, so we have a K and an M, so we could write down our equation of motion here as 5x double dot plus 250x equals 3 cosine 1.05 omega n times t. All right, so we're using the natural frequency to determine our driving frequency, so we should really find out what our natural frequency is. It's still going to be root k over m. It doesn't matter if it's a free vibration or a forced vibration, as long as we're in 1 degree of freedom. So since we're just going to assume everything's in base units here, we're going to get about 7.07 radians per second to be our natural frequency. So our driving frequency, which is really going to be the stuff here, we can then calculate 1.05 times the 7.07 that we just found. We get 7.42 radians per second. Now we can piece together the total solution for this problem now. This is what our solution will look like. In future examples, we'll go into more detail, but here we know that our cosine was on the right-hand side, so we can calculate our amplitude x using the amplitude of the cosine function along with the driving frequency and the natural frequency to calculate our x value. And because we are starting with 0 initial conditions, we know our x of t is going to look like the bottom here, where it will be that amplitude times the difference of those cosine functions. So if we go through the calculations, I won't do them in this example, but we're going to get that x value is negative 0.117, and negative because the driving frequency is a little bit higher than the natural frequency. And we can put together then our full solution for x of t. Because our initial conditions are 0, we're going to get negative 0.117 times the cosine of omega t, 7.42 times t, minus the cosine of omega n times t. So that is what the response is going to look like in this problem. So this is what we'll be able to plot and see what x of t looks like. However, because we have this undamped system and the natural frequency and the driving frequency are close to each other, we also want to think about the beating that's going to occur. And we'll be able to, again, see this in the plot we make. So we want to take the difference between our natural frequency and our driving frequency. Right, so I did switch the order on these. It's not going to matter though because we are doing the absolute value. So we should find our beat frequency is 0.35 radians per second. And we can look at the period of the beat will be 2 pi over omega b. And this is what we'll be more easily able to see in the plot, is what is the timing between these building amplitudes, descending amplitudes, building amplitudes, descending amplitudes. And this is going to come out to 3 digits to 17.8 seconds. So that's going to be this additional period, this additional frequency outside of the driving frequency and natural frequency that our system is going to be responding with. So let's look in the MATLAB at putting this together and making a plot. So just copying down the parameters that we were given, the amplitude of our forcing of 3, again, assuming all base units here are k and are m. Let's just do some of these calculations again to make sure that it's working correctly. So natural frequency, root k over m, 7.07. We are going to have these initial conditions of 0, and then our driving frequency 5% higher than our natural frequency. So we're going to drive this at 7.42 radians per second. And then that beat period and that beat frequency that we just calculated of 17.8 seconds about. All right, so to plot this, I'm going to do it over 5 beat periods that I just calculated. And just so that we're kind of in the heart of the response here, I'm going to start it at the 3rd period and end it at the 8th period here. So I'm starting at 3 times that period and ending at 8, and I'll do a bunch of points in between. I kept it written out here the long way, not simplifying it because our initial conditions are 0, but once we apply those 0 initial conditions on x and what I'm calling v naught for x dot naught when I'm in MATLAB, it's going to have the exact same response we just found that we calculated by hand. And I'm going to plot it. So let's see what this does. What does the response look like? So this is what we get for our amplitude here. So we see this is the beat pattern that we can expect when the 2 frequencies, driving and natural, are close to each other. We have this building up, and then it comes back down to a minimum. Building up, comes back down to a minimum. At the same time, we have these quicker oscillations happening that are from the driving frequency and the natural frequency interacting, and then this slower one that we're going to calculate in a minute, that's coming from that beat frequency. When we have damping, especially as we get to steady state, we're not going to be seeing this beating occurring. This is in these undamped systems where it's happening. So let's see some of these different frequencies that we're observing and get a rough calculation of where they're coming from. So let's zoom in a little bit just on 2 neighboring points. And we're going to be able to see, let's just go from this peak to this peak. Let's go the one before it. Okay, so time-wise, we have a peak at 62.21 and one at 61.34. 62.21 and 61.34. So a time between them of 0.87 seconds. So let's see what frequency, angular frequency, that corresponds to. Will be 2 times pi divided by 0.87. And we get here 7.22 radians per second. And that's pretty close to the driving frequency / natural frequency that we had for our system. So that frequency is actually right between those two. Now again, this particular pattern we're seeing because they're close to each other, the natural frequency and driving frequency. If they were sufficiently far, as we're going to be seeing in the future examples, they're going to be distinct frequencies that we're going to observe. So actually the 2 frequencies we're observing in this system are not the natural frequency and the driving frequency. It's going to be this kind of average of the 2 is this quicker frequency. And as we'll see in a second, the slower frequency we're observing is going to be the beat frequency. So let's see the slower wave that's happening here and try to get a sense of what that timing is going to look like. All right, so I have the time between the peaks. Let me zoom in just to make sure I captured them correctly. All right, so this peak to this peak, which is this slower moving wave, how long does that take? Let's see, 79.97 minus 62.21. Right, so 17.8 seconds between them. We actually already calculated this out. That is the beat period. But just to check the frequency, 2 pi over 17.8, we get 0.35. Again, that was the beat frequency that we calculated. That was the difference between the natural frequency and the driving frequency. And just to check on the other frequency, it is close to the average between our natural frequency and the driving frequency. It's not quite there, but it's close to that average. So in this example, those are the two frequencies that we're observing these oscillations at. Now, we won't always have beating in our system, but we do want to be aware of this phenomenon when we do.